Hello class, today we're going to talk about valence shell electron pair repulsion and hybridization. Our objectives are going to be to understand Lewis diagrams in valence shell electron pair repulsion or VSEPR theory. Our objectives are going to be to explain the properties of these molecules based off these diagrams and the electron properties. VSEPR or valence shell electron pair repulsion and geometry comes under the idea that electrons like to repel each other as lone pairs, creating bond angles. So if you take a look at this atom, the atom tends to have these lone pairs surrounding the terminal atoms, which in turn are going to create repulsions. And repulsions are caused by the idea that these electrons want to be as far away apart from each other because they have a similar charge. Now, because of that, it creates these geometries for molecules that tend to have patterns. So this is generally off of the central atom. So when we take a look at the central atom, we can see that because of the repulsions from the terminal atoms, or the ones they're attached to it, it tends to create bond angles. Now these bond angles are formed from these repulsions, and it's a compression between the atoms that have these lone pairs. As an example, let's take a look at carbon or methane, CH4. Hydrogen here has electrons that's sharing with carbon, and because these don't have lone pairs, they're going to create a 109.5 degree angle between each other. While ammonia, which is NH3, has one lone pair on the central atom, creates repulsion and pushes down the hydrogens further down, creating a smaller angle of 107. Now, had that lone pair not been there, the bond angle would be 109.5. Water has two lone pairs off its central atom, and because of that, the bond angle is even smaller, which is 105. So the idea is that the more lone pairs you have, the more repulsions, which in turn creates smaller bond angles. And let's go back and think about some charts. Now you're going to have to memorize these charts, and these are generally going to be very easy points on the AP exam because the geometry chart is practically just memorizing how many lone pairs you have with the geometry itself. You must memorize all of these bond geometries and their angles for the AP exam. So let's take a look at how you're going to read this. In this example, you're going to have two electron groups for this molecule, and generally it's going to be carbon dioxide as an example, where you have a 180 degree angle. So if you have no lone pairs off the central atom, you're going to have 180. If you have three electron groups, in other words, three things attached to the central atom, whether it be a lone pair or whether it's not a lone pair, it's going to be a trigonal planar or a bent shape. If you have lone pairs, the angle is less than 120, which had one lone pair. If tetrahedral is going to be the other one for the geometry, if you have four things attached, either a lone pair or an atom, you would call it a tetrahedral if it has zero lone pairs at 109. But notice carefully, if you have one lone pair, it'll be trigonal pyramid, and it'll be less than 109, and bent shape will be less than 109.5, about 105. And then once you get to the 5 and the 6, you're going to see that it becomes 5 things attached. In this case, you would have trigonal bipyramidal, seesaw, T-structure, linear, and the bond angles are going to go down to 90, 120, 180. So the magic number here and the trick is to know that's 180, 120, 109, and then 105. So if you're thinking about memorizing these, just always start off with the 180, subtract 60 to get to the 120, and then the magic number is going to be 109.5. One thing they usually will ask you is the pair arrangement. So you're going to have to know linear, trigonal planar, bent, tetrahedral, trigonal pyramid, bent, and then obviously all the way up to 6. Now, to determine geometry is very simple. You're first going to draw the Lewis dot structure. Number 2, you're going to count all the electrons in the lone pairs around the central atom. Lone pairs are part of the electron group, and then you're going to count the triple or the double bonds Then you're going to use the molecular geometry to determine that, which hopefully you've memorized. And then from there, if you have more than one central atom, then you must determine the geometry shape for each central atom and repeat the same. So you may have two geometries if you have two central atoms. So let's go ahead and do this as an example. And I want you to pause the video, do it in your notes, and try to take a look to see if you actually got the same answer. Larger molecules can have two. So as an example, CH3OH has two central atoms, and we're going to have to determine the sketch for these two. So what I would do is draw out the Lewis dot structure for the carbon and then another one for the hydrogen, for the oxygen. Obviously, they'll be the same molecule, but you're going to be having two different geometry for each central one. All right, let's talk about shapes and polarities. So when you're talking about molecular shapes and polarities, we're talking about that unequal sharing of electrons. It's almost kind of like that tug of war. When one atom pulls more than the other, you create the delta partial charges. And a molecule can be polar or nonpolar depending upon the shape of the molecule. And usually if it's a diatomic molecule, if the bond is polar, the entire molecule is polar. And let's take a look at this example. HCl is usually going to be your classic example of a diatomic, meaning there's two elements, hydrogen and chlorine, where the partial charge or delta charge is shifted towards chlorine. And you can see that there's electron distribution on this side. Because of that, it's going to create what we call polarity. So a molecule in the presence of polar bonds may or may not result in a polar molecule. So it all depends on the geometry. So let's take a look at, as an example, some people say, well, because something has a polar bond, it must be polar, and that's not necessarily the case. CO2 is considered to be a non-polar molecule, but it has dipoles next to it. It has a CO and a CO, and because they are moving in opposite directions, they cancel each other out. So although carbon dioxide has polar bonds, it is still considered to be nonpolar because when they go in opposite directions, they cancel out. Now, water is another example of something that has also polar bonds. However, the geometry here is all pointing towards oxygen. So in this example, they have a net dipole moment, and that basically means that they do have an overall shift towards oxygen as your dipole, which would make the molecule polar. Now, a dipole moment is pretty much a set event where a molecule would be polar overall caused by these dipoles hitting in the right direction, heading in the same direction. And so we would actually sum these up. We would sum these dipoles together to create a net positive dipole. Now, generally you will see canceling of dipole moments in linear, trigonoplanar, and tetrahedral geometries with no lone pairs. So keep in mind that those are generally going to be nonpolar molecules because of the fact that they are going to be moving in the same opposite directions. Now, in molecular shapes and polarities, let's take a look at a couple of examples. Oil and water do not mix, and there is a reason for it because of the differences in polarity. Oil is nonpolar while water is polar. That's why it sits in different levels. If you shake the mixture, oil will form within the water, and if you allow it back to rest, they will actually start to move back up. So while oil and water do not mix, the molecules of oil are considered to be nonpolar, and so that affects its solubility. Polar molecules generally will interact with more polar molecules, while we like to use the phrase like dissolves like. Polar dissolves like, nonpolar dissolves nonpolar. Go ahead and pause this video and see if you can walk it through to see whether each molecule is polar or nonpolar, to try to determine a pattern that you actually see based on geometry alone. Now let's talk about bonding and overlap conditions. So in this example, when you have two molecules that are going to overlap, they're going to be doing what we call an orbital overlap. So for example, hydrogen here has a 1s shell that is filling up, and when they overlap, they're going to be combining those orbitals from the first level and the s sublevel. Now, hydrochloric acid or HCl has combining it from chlorine's 3p orbital with hydrogen's 1s, and they'll be creating an overlap with s and p. Now, chlorine's also going to have a nonpolar molecule overlap with the 3p because your highest, remember, we're using your valence shell to actually make those arrangements. This is called quantum mechanics. So when we talk about orbital overlaps, we're in the field of quantum because these electrons are usually going to be in these subshells. And these subshells, as we already know, are s, p, and d. When these two nuclei are starting to overlap, they're going to create a new kind of bond that's going to overlap between these two. And as these orbitals overlap, the electron density becomes concentrated in that area between the nucleus, which in turn allows them to be both attracted to both nucleus, forming a covalent bond. So a covalent bond really is a hybrid of these orbitals. Now, let's talk about how we're going to define these using quantum. Now, sigma bonds are basically a way to show a first bond between two atoms. The best way I like to think of them as that they are single bonds. So sigma, single. Pi bonds are generally going to be second or third bonds, and generally they're going to be overlapping of p orbitals, and those are generally going to be 1 sigma for singles, 1 sigma and 1 pi, and triple is always going to have 1 single and 2 pi bonds. So let's take a look at this example right here. Hydrogen has a single bond, so it's going to have 1 sigma. This molecule has 2 carbons with a double bond. It would have a pi and a sigma. And this one would have 1 pi and 1 sigma for N triple bond. And so the example here is the overlaps are going to be on what we call this internuclear axis. So think of it as like this plane in which these orbitals are going to be housed in. And when they combine together, they're going to be called these new bonds, sigma, pi bond, etc. And you can kind of see this carefully with the sigma bond and the pi bond, that they're going to be overlapping in many different ways. So here is our carbon bonds overlapping. You'll be making your sigma and your pi bonds. Your pi bonds are generally going to be at the very top, and then your sigmas are in the middle of that internuclear axis. Pi bonds generally is an overlap above or below the internuclear axis. So this is going to be our pi bond right here. And generally, that's going to lead us to this idea called hybridization. Now, the word hybridization means a combination of two or more things. And generally, the orbitals basically means that there is going to be some sort of new orbital that's being mixed in to create that. And we usually denote that using this idea called hybrid orbitals. And a hybrid orbital is different from the shapes of the original orbital. So if you take a look at hybridization here as sigma being a sphere, and a pi bond being on the x-axis, when you combine them together, you're going to be making 3 new orbitals, and these are going to basically be hybridized. So in this example right here, we have 3 orbitals, 1 along the x-axis, 2 along the x-axis, and 3 along, actually all along the x-axis, but they are shaped differently. And in this example, they're going to maximize overlap. And the hybrid orbitals also are going to include lone pairs on the central atom. So in a nutshell, what hybridization means is that when you create these new orbitals, you're going to actually make a new shape. And we call these sp hybridizations. So let's go over as an example. So an sp3 hybridization orbital is basically a orbital that has 1s and 3p orbitals. So if we take a look at this example right here, we have 2s and 2p3. When you mix them together, you'll be forming sp3 orbitals. And so the idea here is you are actually going to be combining them together to make a new subset. So where do they get these numbers from? Well, basically what we do is we look for things that are being attached to the main orbitals. Now, without going into detail, because the scope of the exam is just, can you figure out what that is? If I have an sp3 orbital, generally I'm going to have 4 things attached to the central atom. So for example, this CH4 molecule will hybridize to form sp3 because it has the 3 in the s or p orbital and 1 in the s, so that's basically an s hybrid. There's 4 of those between the carbon and the hydrogen, but they're all pretty much the same. So we're going to call these sp3, because if you take a look at carbon actually has up to its p subshell filled. So we would actually have your p and your s for carbon hybridized to form your sp3 hybridized with hydrogen. And so same idea with this kind of NH3 molecule. NH3 also has sp3 here. The nitrogen has these sp3 lobes, and that is going to be combining with that 1s for hydrogen as well. So we're technically looking at that central atom to determine what those are. Now the easiest way of remembering this is that if I have 4 things attached, I'm going to be using the p and the s hybrid, because generally that molecule will have enough electrons for each one. Now, sp3 hybridization seen has 4 electron groups, and I'll call it 4 things because it can include a lone pair, and this includes tetrahedral, trigonal pyramidals, and bent geometries. Now, sp2 hybrid is even easier. sp2 hybrids are basically going to be molecules that have only sp2s. So the example here is they're going to have a mix of 1s and 2 p orbitals. And so basically when we look at these problems, we're going to be looking at one unhybridized p orbital. And so the remaining unhybridized p orbital can be form a double bond, one single or one pi bond. And the sp3 usually has 3 electron groups, which includes trigonoplanar and bent. So again, usually you include 3. The magic number is 3 because s has 1 and p has 2, so we're going to include it to 3. Now again, for the scope of the exam, just draw the geometry, count the central atom, see how many things are attached, and you're going to get your hybridization. All right, sp orbitals are going to be very similar to sp2. The only difference is we're probably going to have only 2 things attached. And the example here is you're going to have 1s and 1p with 2 leftover unhybridized p orbitals. And so the idea here is the remaining p and can form a triple bond, 1 sigma and 2 pi bonds. And you're also going to see 2 electron groups, and usually you're going to find them in linear geometries. So again, these are going to be the 180s degree angles, and they're going to be hybridized with your sigma and 2 pi's, usually for triple bonds. As long as there's no lone pairs in there, you're fine. Okay, so just to recap, there's a lot of theory. You must be able to look at the Lewis dot structures to determine the hybridization, which is dependent upon the number of electron groups and determine the number of sigma and pi bonds. This is a very classic type of question. Go ahead and pause the video so that you can do this yourself. It says determine the hybridization for each of the level atoms in the diagram below. Usually they'll ask you for how many pi bonds and how many sigma bonds, and then they'll ask you for hybridization for those. So again, 4 electron groups, sp3, 3 electron groups for sp2, and 1 for sp. So if I were to take a look at atom 1, this would be sp2, and the reason is because I would actually have 3 electron groups, 2 lone pairs, that's 1, 2, and then your double bond, which would be here, would actually count as another electron group to the carbon, that's sp2. Now number 2, this is also going to be sp2, and the reason is because you have 3 things attached, the carbon, the hydrogen, and the sulfur. That's sp2, even though it's a double bond, because double bond counts as like 1 unit. Carbon here, this one would also be sp2 because Sc and O, and the O, that's sp2. And finally, 4 would be, this is actually an sp3 because there's 2 lone pairs and a carbon and a hydrogen. And the question is how many pi sigma bonds are in the entire molecule? That would be 6. Now the reason there would be 6 is because if you count how many single bonds you have, 1, 2, 3, 4, 5, 6, you actually are going to have 1 pi bond, 1 here, that's 1, sigma bonds, 1 single bonds, 1, 2, there's 3, 4, 5, and 6. And so each double bond would have 1 sigma. Now how many pi bonds do we have, which are basically going to be the ones in the double bonds? That should be 2, 1 and 2. So hybrid orbitals is, go ahead and pause the video so that you can try it yourself to consider how many of these atoms are labeled, and go ahead and pause it. Okay, so let's go over the answers real quick. So let's consider the following. For atom 1, I'm going to ask what is the hybridization for that. So in this example, I have 1, 2, 3, 4. There's 4 things attached, so that'd be an sp3. For 2 would be 3 things attached, double bond with oxygen with a carbon-carbon, that would be an sp2. 3 would be 1, 2, 3, 4. That looks like there's 3 things attached again, sorry, sp2. Number 4 would have only 2 things attached, so because of that, that would be sp. And number 5 is we have 1 lone pair, another one that's also an sp orbital. Now on this side, determine the hybridizations for each one. So let's take a look at number 1. This one has 1, 2, 3, so it'll be sp2. For number 2 would be 4 things attached, so it should be sp3. And finally for 3 should be 2 things attached, would be sp3. 2 things attached plus the lone pairs, which would be sp3. So 1, 2, 3, 4. Just be very careful with the lone pairs. Sometimes we tend to forget those. All right, so consider the simplest amino acid, and we're going to pause this video so that you can try it yourself, and then go ahead and see the answers afterwards. So in summary, VSEPR theory uses Coulombic attractions or repulsions that predict the arrangement of electron pairs. Both Lewis diagrams and VSEPR allow you to predict electronic and structural properties, including molecular geometry, hybridization, bond lengths. They also have this idea called hybrid orbitals, which involve bond angles, and we also know that there's sp2, sp3 bond angles as well. And then we also have this idea called sigma and pi bonds, which are part of this atomic orbital. So this actually helps create attractions and also helps strengthen the bonds as well. So hopefully you enjoy this. I'll see you guys next time.